Again, like I was saying earlier, basically the emphasis right now on exam 2 is on this 3 chapters, 24, 25, and 26. And the idea behind them is circuits. While you're doing the chapters, you really don't see probably where we're headed. You don't see where are the main points are. So by the time we finish this 3 chapters, which I'm hoping to be done by Monday, okay, this coming Monday, which should be clearer. It should be really, we know exactly what is important in terms of energies, in terms of calculating, for example, power, dissipation, and resistor, and so on and so forth. Okay, so it should be clearer for you guys down the road where we're headed with these things, and it should be. Besides, you already have homework assignments, so I'm hoping that you guys are spending the time to do those. Okay. Now the homework is different than the first exam. It's due before the exam this time around because I noticed that at least some of you did not go through all of them as they should have, and they're really the essence of all of your preparation in terms of concepts and things like that. I already stated the fact that you will have another quiz, which is also covering the 3 chapters. The quizzes are actually has twofold goals. First one is to assess your knowledge of these things. And the second one is to prepare you because they focus specifically on the exam concepts. So basically to help you prepare for the exams. So that's the idea behind all of the stuff I do with you guys. And I'm hoping that you guys I mean, you find this approach kind of useful for you guys to help you guide through your class. Physics 2, as I said, from the get-go is not the easiest physics in terms of the calc-based sequence of the courses that you will have in any college. It's not just in Norco. And it's really, unlike, for example, Physics 1, which is kind of intuitive a little bit. You can always imagine what an incline looks like, and if you drop a ball on it, you can, in your head, basically envision what that ball will do. So you're, in a sense, guided by that intuition, and that's helpful. That's very helpful because sometimes you find an answer and you know, oh, that doesn't make sense. So you work your way backward trying to fix the issue, and it fixes usually. Physics 3, which is in this college, is thermodynamics and also optics. Optics is a really day-to-day experience, so that's really not hard to talk about. For example, images, how they form in front of a mirror, and how you focus an image, for example, using lenses and things like that. So if somebody tells you a camera, what would you do to focus an image? You probably move back, changing the focal length of the camera. So physics 3, in a sense, is easy because it deals with stuff that is day-to-day. In terms of thermodynamics, also, somebody tells you have a hot object in here. I have my coffee in front of me, and I have a cold water in here. If you put them in contact, the heat, there is a heat exchange. So again, there is the intuition that works to your advantage for physics 3. Physics 4 is a little bit kind of hard in a sense conceptually because it deals with relativity and also quantum mechanics. But the math behind it, there are only a handful of examples basically that you can find in any textbook. So you're going to pull them and you're going to do them, and that's the end of it. So and sometimes when you have very hard also to imagine something and the math behind it's kind of easy, straightforward, so you don't really have to deal with a lot of things. Physics 2, on the other hand, you have to deal with the concepts of fields, which by themselves require a little bit of an imagination, okay? So you don't touch an electric field, for example. You don't have day-to-day experience with it with your hands on. You don't see it. But of course, you experience. The only reason why you see something is because of the electric field interacting with your retina, okay? But you don't have that intuition. That's one thing. For same thing with the magnetic field. I mean, you play with magnets all the time. But the magnetic field itself, yes, you can take a compass and go around and find which way it points. But again, you don't have that intuition, unlike, for example, the inclined plane and all the things. That's one problem. The other problem is the entire course is a vector-based calculus, which probably you did not do yet in calculus yet. And even if you do it in calculus, it's not the easiest math that you will be dealing with. So conceptually, I mean, it's hard. Mathematically, it's hard. And the examples, they can be very, very, very complicated, and there are a variety of them. So that's why this topic is not easiest in the world. I'm telling you that not to discourage you, but to tell you that basically that is hard. But if we put ourselves to it and do all of the problems and everything else, we should not have difficulty with these things. That's why I'm trying to be upfront with you guys, and this is the truth, okay? So I'm hoping that you guys focus on these materials and try to understand. Fortunately, we're in the part that a lot of people enjoy right now, which is electricity and circuits, okay? That is the part that is, again, you turn the switch and the light goes on. So that's something that we kind of, it seems like a lot of my physics 2 students tend to enjoy, and they get a lot out of it because it's mainly algebra, actually, okay? So for those who are...
Professor?
Yes.
Oh, I have a question. Would you, for the upcoming test, would you say it would be out of your previous classes that you taught for this, for Physics 4B, would the second test be would be one that students understand more and get?
Yeah, usually the first test is the hardest in terms of, that's a good question, actually. The first test is, it's kind of hard because a lot of people, they think that it's one thing and they get it in a different thing. By the time the second test comes in, usually it's kind of, it's a lot better than the first one in terms of grades. The third test is similar to the first test because you're dealing with fields again, and instead of dealing with Gauss's law, now you're dealing with Ampere's law and all kinds of things. So you have to be very careful with the second exam. I mean, the third exam. The fourth exam is actually a little bit easier too. It's usually, technically, honestly, the second exam is the easiest of the bunch, okay? Followed by the fourth, and then the first and the third, they're kind of a little bit higher because of the fact that you have to deal with vectors and projecting the vectors in one direction and the other, and using the symmetry to argue one thing is canceled and one thing is not. So you have to have that little bit of math combined with physics, and you have to have an approach to it. That's why I suggest that you guys, when you solve the problems, you really follow the scheme. And again, you're losing points if you don't do that when you solve the problems, because you're trying to analyze the problem at the end, because it helps you toward other situations that you can have. You think through the problem outside of that. So again, to answer your question, technically the second exam is actually the easiest of the bunch. What I do in my other physics classes when we were face to face, since I don't do makeup exams, basically, if you miss the exam, that's it. You get nothing in it. I dropped the lowest grade, including the final, and the final is comprehensive from chapter 21 all the way to chapter 32. So, we'll talk about the final. The final review actually has to do with all of the exams before. So if you go and review all of your exams and see exactly how these things work, chances are you're going to do well in the final. So that's basically how this, at least in terms of my testing approach is. And you notice already that you're tested in different angles as far as my classes. You're tested in terms of quizzes. You're doing also basically solving problems and turn them in terms of homework, doing the same thing in terms of exams, and also labs. You're being assessed, and you also are being assessed on your participation for the class. So by the end of the class, this different approach in terms of assessing your basically taking these materials. I'm hoping that you guys will really basically advance toward physics 3 or whatever you guys need out of this class. Okay. So.
Thank you, Professor.
No problem. Chapter 26. Okay. I know I talked about some of the ideas in chapter 26 last time around when we had lab. We have quite a few people now, so that's good. So I'm going to go back to those things again because we need them in this chapter. Let me get one note again, open a new tab in it, and go back into here and share that screen. Let me stop sharing again. Let me share again. Here is the screen. So the idea that we had in lab was the following. If I have two resistors, a 10 ohm and a 5 ohm for me, or a 10 ohm and a 10 ohm, just to follow the same argument that we did before. So I have a 10 ohm sitting in series with another 10 ohm. Okay. So again, there is a voltage between points A and B, and that voltage is a given value. So VAB or VBA, doesn't matter. In my notation here, it's VB minus VA. And this is another 10 ohm, by the way. So that's the voltage drop across the entire end-to-end, basically. So my argument then, if you guys remember from the lab from last time, that Monday, is that we do the same thing as we did for the capacitor. Think about it the following. You want to come down from the 3rd floor all the way to the 1st floor, okay? Either you jump straight out, which is fine. I mean, as long as you have super strong feet, or you go jump to the 2nd floor, and then from the 2nd floor you go to the 1st floor. So you have that approach. Same thing in here. I'm trying to find the drop in potential. Did they put it? I'm sorry. This is supposed to be VA minus VB, because the way I drew the electric field there indicates that this is actually a higher potential than the other one. So I'm dropping in potential. Same thing. This is my 3rd floor. I'm dropping in potential, and I'm going to the 1st floor. Okay. So the drop in potential can go straight out, or you can go through an intermediary point. Of course, if you're coming from the 4th floor, then you can go from the 4th floor to the 1st, or from the 4th to the 3rd, then the 3rd to the 2nd, and the 2nd to the 1st. You have different ways of getting from the 4th floor down to the 1st floor. I'm taking a point in here, intermediary C, and do the same analysis in here and use as if. So we're doing VA minus VB, okay? So the potential drop between A and B is VA minus VC plus VC minus VB, okay? Again, and I mentioned that when we were doing the capacitors, if you don't know anything about this electrical stuff, you could look at this expression and say it makes sense no matter what VC is, okay? So that's basically what he's saying, is the drop in potential between A and B is the same drop in potential between A and C, added to it the drop in potential between C and B, okay? That was a question that a long time ago, I think, Faraz asked when we were doing the capacitors, and this still holds true for the, because it's a drop in potential. The analogy with the height is not just semantic, it's not just basically picture, but it's actually very close, because the electrical potential, well, in terms of, in this situation, in terms of electrostatics, is no different than the gravitational potential when you do gravity. So the analogy is very close. The only trouble there in this is that in the case of gravity, masses always falls from the high point to the low point, because masses are positive. So when you drop a mass from a higher point to the lower one, it's always going to fall. Now, charges, they always also fall from the high to the low if they are positive. So proton, if you drop it in here, it's going to actually fall the way that you have it. So it's going to fall like the masses fall from the 3rd floor. So a positive charge will do that. A negative charge, though, that's the problem. The analogy stops. A negative charge will fall actually upward, okay? That's the direction with which the negative charge falls. If you have that in mind, you should be fine. If you remember this thing in here, you're going to be fine, okay? Unfortunately, I mean, in real life, we don't have negative masses. If we had negative masses, they will be actually stuck in the ceiling, okay? So think about it. I mean, if you have positive masses and negative masses in your house, the positive masses will be on the floor because of gravity, and the negative masses will be in the ceiling. So that's basically how you can think about it. To bring back the analogy in there. Okay. So that's basically the points in here. Now I know from Ohm's law, and this is a big deal that we discovered last time, okay, that the drop in potential across a resistor is the resistance times the current. And I said that the conservation of charge indicates that the charge that must go through the first resistor must be the same charge that comes from the other side of the resistor. Since that's the same charge, it's going to go through the second resistor and come out from the other end at any given point. So the rate at which these charges are changing with time is actually the current. So the current is the same throughout an entire circuit, which is the rule for parallel circuits in series. The currents are the same, or the charges are the same. That's the same thing. So I is the same. That's what we're saying, that they are in series. This is equivalent to saying that they are in series. Okay? So if we do that, then this is nothing but just R1I, and the second one is the same thing, R2I, and both of them add up to the entire potential, which for me, if I didn't know that this is the actual configuration, it looks like I have 2 points, point A and point B, and between them, I have a big resistor, which is the equivalent of both of them. So R equivalent times the entire voltage drop, times the entire current, I'm sorry, which is the entire voltage drop. This is the voltage drop between A and B, between this point and this point. It's the resistance times the same current that goes through both of them. It's the same current I. So that is the voltage drop from A to B must be equal to the voltage drop across the first resistor, which is by Ohm's law is this expression, plus the voltage drop across the second resistor. Of course, the current in here is I. As long as it's not zero, I can cancel the entire I from both sides, and I end up basically with R equivalent being just the sum of the R's. And if I have 3 resistors, it's going to be plus R3 and so on and so forth. Okay, that's one of the results we discussed on Monday when they're doing the lab, and it's critical for our lab. The second result has to do with the circuits in series, in parallel. So the resistors in parallel, basically they have the same potential. In series, they have the same current. In parallel, they have the same potential. So this is the first resistor, which is my 10. So to go back to numerically speaking, so if I have a 10 ohm and a 10 ohm, and I put them together, they end up being 20 ohms. Okay. So this is my first resistor. I put it in parallel with the second one, making sure that the current, when it comes in here, makes what is called a junction, okay, or a node. So in here, again, it's another junction where the current splits, where the current actually joins again. And between points A and B, I have the same potential, VAB. But in here, I have 2 choices for the potential. I can go this way. That is the same VAB as much as I go this way. It's the same potential VAB, okay? It's the same potential between the 2 points because these wires have no resistance. So since the wires have no resistance, this entire point is the same B actually. If you like, this is B, everywhere you can think about it, this entire region is B. However, from here to here, there is a device, there is a resistor. So it's not B anymore, it's actually A because this entire wire has no resistance. This is the same point A. So this is why I'm saying in here, the voltage drop in parallel is the same. So unlike the currents being the same for the series, for the parallel, the voltages are the same. The voltage drops are the same. So this is the same thing as saying parallel. Okay, that's the opposite. So currents or chargers are the same for series, whereas in this case the voltages are the same. So now I write the expression for the voltage drop using Ohm's law. It's R1 times this current now, which is probably I1, not necessarily the same because the resistors may be different. And this is R2 times I2. Okay, so that's the relationship that I need now. So the voltage is being the same between A and B indicate VAB is the same thing as R1 I1 and the same thing as R2 I2. Obviously, I need to find an expression for the equivalent resistance. So now what I can say is the following. If I didn't know any better, if I didn't know that there were actually 2 resistors in series in here, in parallel in here, what I could have thought that this circuit looked like is just I have point A and then I have point B, and between them I have an R equivalent. Okay? So in that case, there is a current I that leaves point A, the higher potential, and ends up in point B, okay? So in that case, what I say in this case is that actually the same potential drop, this same thing, is R equivalent times the total current I. And the current I must be the same because I, when it leaves point A, is actually split between I1 and I2. And I'm just arguing that the charges don't get destroyed or processed in the process. So if 3 coulombs move on one way, 7 coulombs move the other way, that means what I have actually drained from the side of A is 10 coulombs. So what I'm saying in here is that I is simply I1 plus I2. use this expression to find I1 in terms of VAB. Use this same expression now to find I2 in terms of VAB and R2. And use now this last expression in here to find what I is in terms of VAB. So everyone will have a VAB. So this relationship now will give me I being VAB over R equivalent. So this is the same thing, VAB. And I1 from this relationship will give me VAB over R1. Okay, my mouse is. So this will be VAB over R1. And the last one, the same thing, will give me VAB over R2. So now this VAB cancels from both sides of the equation, and I have 1 R over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 if I have actually a third one, and so on and so forth. Don't forget, and this is critical when you're doing problems, to invert the inverses. Okay, so this is completely opposite to what we did when we were doing the capacitors. The capacitors in series, the equivalent capacitors is the inverse of the sum of the inverses. Okay, and the capacitor in parallel is just the sum of all the capacitances. The resistance is the opposite. Okay, so I want you to, in your notes, to write this table. Please open it and do the following. In here, you're gonna write capacitor in the second column. The third column, you're going to write a resistor. In the fourth column, you're going to write an inductor, because we're going to get another device in here, inductor. Okay. So for right now, just write the word. You don't worry about the rules for it. In here, in the rows, we're going to write series. And in here, we're going to write parallel. This table should help you visualize where things are. So capacitor in series is an inverse law. So basically, C equivalent is the inverse of C1 plus C2 plus so on and so forth, inverted. Okay. Whereas the resistors is just the sum of the resistors. It's R1, that is R equivalent, is R1 plus R2 and so on and so forth. Here, we're going to leave it blank for right now because we didn't reach that device yet, okay? It's not part of this exam, the inductors. They are part of the next exam. So don't worry about it for right now. But leave it so that at some point in the future, we're going to come back to this table, okay? I really want you to really connect back all of the devices that we're going to learn in this point in here. In the case of parallel for the capacitor, C equivalent was simply equal to C1 plus C2 and so on and so forth, okay? In the case of resistors, it's like the other expression. So it's R equivalent is equal to 1 over R1 plus 1 over R2, and so on and so forth, and at the end inverted. Okay, and again, we're going to leave the case when we have inductors, and we're going to put them in series. I mean, in series and also in parallel. So for right now, this is the only two devices we know. Okay. So this is important in terms of how we connect devices. Before I move on into more circuits, there is a point that we missed from last time, and namely the effects of temperature. Okay, and I know I mentioned that in the lab. And the fact that resistors, they heat, and where then temperature increases, actually their value changes. And that is because experimentally we noticed that the resistivity is not a fixed value with temperature. It's related to a change in temperature with this expression, 1 plus an alpha, which is a characteristic of the material itself. This is for a specific material, times the change in temperature, or the difference in temperature between it and some nominal temperature. Usually in the tables, they list T naught as being room temperature, 20 degrees Celsius, okay? So if T naught is 20 degrees Celsius, then alpha is the value that they give you in here. So alpha has the units of 1 over temp, 1 over degrees in this case, okay? Sometimes they list it in Kelvin, but don't worry about it because the difference in this case doesn't matter whether it's in Kelvin or in Celsius, okay? Because the difference of temperature, delta T, is in Kelvin, is the same thing as delta T in degrees Celsius. I've never seen it listed in Fahrenheit, so that you guys know. Okay, so some of the problems probably you encounter in the book are going to have the expression into account. Now, again, if I multiply the expression by L and divide it by A, so it's going to be on this side R, okay, is equal to R naught times 1 plus the same alpha times the change in temperature, whether in Kelvin or Celsius. Now, sometimes they don't list it in they don't give you alpha when T naught is 20 degrees, but they give it to you in terms of when it's 0 degrees Celsius. Then you have to use that expression. But remember, T is not the difference is from T minus 0, basically Celsius. Okay, so you have to remember that in your calculation. That's the only thing. Now, when you do physics 3, I mean, what is it? 3C, that is, okay? When you do 3C, okay? We call it physics 3. When you do 3C, you will be dealing with thermal effects and temperature and heat and things like that. And you will notice there they urge you, and they actually not urge you, they require you to use the Kelvin, because all of the expressions they will use, most of the expressions they will use the Kelvin. It doesn't matter, okay? So if that's the case, just please them, and T naught then can be either a 300 Kelvin or 273 Kelvin, whichever number that they give you, so it's fine. 273 or 273 or 293. Room temperature is 293 Kelvin. I'm just telling you this so that to look forward into problems in the future, they might give you a heater and you're doing devices in physics 3C, so you have to remember this expression when it comes back to it, okay? So this is something that we didn't discuss in lecture last time around, but this is something that you have to have in mind. Now, this expression rho naught is the resistivity at room temperature, at this temperature, or at 0 degrees Celsius, whichever they give you. Alpha is the same value. Alpha is constant, okay? They give you alpha and they're constant. And again, this is not a law. This is an approximation based on observation, okay? This is not really, to be honest with you, a law. But the fact is, the resistance changes with temperature. So if you have a resistor in the lab and you're doing your lab, you have to be very careful with it not to leave it over time heat while you're collecting data, because that device, its resistance will change and the dependency of Ohm's law becomes nonlinear. It's no longer V equal to Ri. I mean, it's still V equal to Ri to some extent, but not in the linear fashion, okay? Not a line. This is clearly, it looks like it's this line, okay? Where the slope in here is the resistance itself. If this is I and this is V, okay? But R itself is changing now, so you'll have different readings for the voltage if you're changing the current or vice versa. So you have to be careful with this expression in here. So that is in terms of the stuff that we have covered so far in the lab and basically the lecture from last time. Okay, the main things are the two expressions that will help you, at least in terms of your exam and homework, are Ohm's law, of course, from this chapter, chapter 25. In addition to the expression of how R and rho are related. Okay, this expression is important. And also in terms of the energy also, okay, the power, I should say, it's Ri squared. And we said in general, actually, this is Vi. So this is true statement all the time, okay? In the case of resistors, it's this much. So that's the power dissipated in the resistor. And then we discussed the parallel and the series circuits, which we just did, which are important also for your exams. Chapter 26 has a big deal on two things that we really need to cover. First of all, Kirchhoff's rules, okay? They are essential to doing circuits, okay? Kirchhoff's rules. I don't know how many H's and how many F's he's got. Probably he's got a ton of them. Okay, I really have to look at the spelling for this guy because he's... Do I have it in here? No, that's chapter 26. I'm sorry. I don't have chapter 26 in here ready yet. Oh, hold on. Yeah, there are 2 H's and 2 F's, as I suspected. There are a bunch of them. There are a million H's and a million F's. Okay, so there is another H in here. That's the second F, Kirchhoff's rules. Okay. And we already did them, except we didn't state what they are. Okay, we didn't put them in verbatim. Okay, so the first rule is the node rule. Sometimes it's called the junction rule. Okay. Basically, here is expression for it. Sum of all the currents is 0 in a junction. That's basically how it is. The only trouble with this expression is it's an algebraic expression. Algebraic expression, meaning some currents are positive, some currents are negative. If we think that all incoming currents are positive, then all outgoing currents are negative. The sum is 0. That means all the incoming are equal to the outgoing. Here is a junction. Okay, like similar to the one that I was drawing earlier. And then here I have 5 wires coming out of it, for example, okay, in the junction where 5 wires meet. So I have 5 wires meeting in the same place. And I start looking at currents. Anytime a current is coming, and I'm going to give it a positive sign. So this I1 is positive. This I2, for example, is positive because it's coming. I3, on the other hand, it's leaving, so I'm going to say it's a negative value, okay? I4, for example, it's coming also, so I'm going to assume it's positive. So again, that's my convention in here, okay? Your convention could be backward, and that's fine. The sum is still 0, okay? And this one, I5, I'm going to assume also that's leaving the junction, so I'm going to append to it a negative value. If I assume, what this law is saying then is the sum of all of these currents is equal to 0. That means I1 plus I2 minus I3 plus I4 minus I5 is equal to 0. The reason why this is true is because there is no accumulation of charges in the node. So if charges are coming in here, not some of them decide, you know what, guys, I'm tired, I'm going to sit in here and you guys continue. No, charges must, if they come in there, they cannot accumulate in that point. That's number one. Number two, also, charges do not appear out of thin air in a junction. Not, for example, 5 coulomb came in, and all of a sudden, 6 coulombs emerged. There is no way that's going to happen. So this has to do with the conservation of charge. So this expression is the conservation of charge. So the junction rule is very simple. The sum of all of the incoming currents and all of the outgoing currents are the same. Because if you can clearly move the negatives to the other side and keep the positive on this side, I1 plus I2 plus I4 are actually incoming, and they're equal to I3 plus I5, which the way I gave that example there are outgoing. So all the incoming, namely I1 and I2 and I4 are incoming. So they're equal to the outgoing, in this case, I3 and I5. And there is a reason for it. It's because charges are not created in the node and they are not destroyed in the node. So the node has no business in here with the creation or making charges or destroying charges, and that is the charge conservation. So this is the junction rule. Again, all incoming currents add up to the outgoing currents. These are called rules because they are not called laws, because again, they are practical in terms of working with them in terms of the circuits. Granted, these rules are only true in the case of time-independent phenomena, namely electrostatics, okay? The fact that these currents are actually steady. So you have to take that into account too, okay? That's rule number one. Rule number two is called the loop rule. So the first one was a junction rule. The second one is a loop rule. So, rule number 2 is the loop rule. So I have a starting point in here. It doesn't matter where in the circuit. So I have probably a bunch of devices, and I have a resistor in here, I have a capacitor in here, and I have a million other things. A battery probably in here, I have a switch in here, okay? And I have probably another resistor and a bunch of other things. The point being in here, this is a loop. Your starting point is the same as your ending point, okay? So you start from here, and you come back to the same point. Word of caution in here, the starting point can be anywhere. It doesn't have to be a specific point. In a loop, the starting point can be any way you choose it, number one. Number two, the direction is up to you. You can go clockwise or counterclockwise. It's up to you. So you can go clockwise in the loop or counterclockwise. The only problem is, at some point, you probably are going to be going higher and higher in the potential, rising in potential, and sometimes you're going to drop in potential. That's the only thing you have to pay attention to when you're doing that, okay? So what the loop is saying in here is that delta V is equal to 0 in a loop. In a loop, delta V is equal to 0. You go around, let's say, for example, you go from the 5th floor and you're keeping track of which floor you're in, okay? Did you gain floors or did you lose floors? You go down to the 4th floor, okay? Now you went down, okay? 1 floor. Then you go another floor, for example, to the 3rd floor. You went another floor down. And from 3rd floor, for example, you went all the way to the 1st floor. So you skipped the 2nd floor. You went 2 floors down, okay? So now you have a total of 5 floors down. Then you went up from the 1st floor all the way to the 6th floor. So now instead of going 5 floors down, you went 5 floors down plus 6 up. So you ended up with 1 floor up. You guys understand above where you're supposed to be. And then at the end, you went 1 floor down from the 6th floor back to the 5th floor. So the question at the end of the day, how many floors did you go up and down if your starting floor is the same as your ending floor? The answer is the same thing. There is no gain or loss in floors. Do you guys understand the analogy again with gravity? So somebody is carrying a piece of paper and keeping tracks of the floors, and the other guys are moving around. If your starting floor or starting height is the same thing as your ending height, then in this case, you ask yourself, did we go high or did we go down? The answer is obvious, since your starting point is your ending point, is you didn't go higher or lower. At the end of the day, you stayed in the same level. You stayed in the same height. You guys see the point or not? With the second rule. Okay, that is the task of the day. You're going to summarize both rules for in your own words for Kirchhoff's rules. You're going to tell me in your own words, with your own analogies or whatever at least you show me that you know what you're talking about in terms of the loop rule and in terms of the junction rule. You guys understand the task of the day? Okay, you went to 2 different floors. It doesn't matter, but at the end of the day, Daniel, your starting floor is your ending floor. Okay? So you could have gone from the 5th floor on apartment 5C, for example. 5C, for example.
Yeah, but the resistors act like the floor, right? And or the capacitors.
It doesn't matter.
No, but in the analogy, that's what you're saying, right?
No, the resistors are just basically the neighbors that you're gonna meet down the road. Okay.
Oh, okay.
So you're visiting them, giving them flowers and giving you whatever they want to, and then you're coming down from the 5th floor, apartment 5C, okay? And you went down to 3rd floor, to whatever, and then you ended up using the elevator all the way to the 6th floor, okay? Visited some neighbors in there, and then you ended up in another apartment in the 5th floor, for example, 5D, okay? You don't care about the apartments, saying they're both on the same floor. Your question was, somebody carrying with you, did we go at a higher level or lower level? But if your starting floor is the same as your ending floor, and your starting height is the same as your ending height, you didn't gain anything. You didn't gain any height or lose any height. The same thing with the potential now. You guys, does it make sense to you guys?
Yeah.
So it doesn't matter what you encounter on your way, okay? There is probably bandits and there is probably other things. That's not relevant. The person doesn't care about that. He's just keeping track of the height, okay? That's the only thing he cares for. Same thing with the potential, okay? So those are the two rules. So the node rule has to do with the conservation of charge. The loop rule has to do with actually the conservation of energy. Because remember, height is energy, and the potential, if I multiply by charge, I am really doing the energy, because the same thing, I'm keeping track of energy. So in this case, it's a conservation. Oh man, did I forget to put this? Am I sharing the right screen or not? Conservation of energy.
Yes, you are, Professor.
Okay, thank you very much. Okay, so that is basically the point in here. What we're talking, the first one is conservation of charge. The second one is conservation of energy. And because they are not really laws, they are laws that we know. I mean, the charge and the energy, they are fundamental laws that we use. So basically, it's a restatement of those same laws, a rewording of the same laws. So those are critical. Yes.
Professor, could you repeat what the discussion questions were?
The discussion is to put it in your own words.
And
the Kirchhoff's rule, number 1, which is the loop rule. I mean the junction rule. That's rule number 1. That's the one that talks about the conservation of charge. All the incoming is equal to all the outgoing. That's rule number 1. Rule number 2 is the loop rule. Okay, this is where the conservation of energy is. Okay, gain heights, lose heights, whatever that is. So those are the 2 points. I want you guys to put them in your own words. Okay, because if you're gonna do any kinds of circuits whatsoever, okay, you're going to be doing them all over. And as a matter of fact, in this class, they're going to be extremely useful and used a lot. So in your circuits, okay? For example, let's take a practical example quickly in here and see if we can do that, okay? See if we can take advantage, leverage this thing in here. So I have a battery in here. Remember, this is the symbol of the battery. I'm going to make it simple, okay? I'm going to take a 12-volt battery, okay? I have a switch in here. Usually it's a good practice to have a switch somewhere, okay? I have a resistor in here. I'm gonna make this resistor to be 5 ohms, okay? I have another resistor in here, okay? I'm gonna make it a 5 ohms too, okay? And I have another resistor in here, and I'm gonna make it 5 ohms still, okay? Or let's make it an interesting thing in here. Let's make this one 10 ohms, okay? Make it a little bit higher than the others. Here is the question. They want to know when the switch is closed, okay, how much power is dissipated in the 10 ohms, P10, okay? The first question to ask is, how many loops do I have in here? Do I have any junctions first or not? Do you see them or not? Here is a junction. Okay. Here is where the current actually split. And there is another one, you're absolutely right. So this one actually is another junction also, where the current actually come back together again. Okay. So those are the 2 junctions. But they're actually the same junction. Let's think about it why. So the current that leaves the battery when the switch is closed, I'm going to call it I. Okay. It's the same current that leaves this resistor, again, because of conservation of charge. So this is I. Now it's going to split itself between this I, which I'm going to call it I1, and this I, which I'm going to call it I2, okay? When I1 emerges off of the other side of the 5 ohms, it stays I1. So this is still I1. When I2 emerges off of the 10 ohms, it's still I2. Now, I1 plus I2 must be equal to the I that came in here in this junction. It says I is equal to I1 plus I2. That is basically what the Kirchhoff's rule number 1 is. So Kirchhoff's rule number 1 states that I on that first junction is the same as I1 plus I2. Okay. On this side in here, since this battery is delivering a current I, so it must be also taking the charges from the other side at the same rate, I. So this is I also because of the situation here what's going on in the battery. So if I use Kirchhoff's rule here, all the incoming are I1 plus I2, and the outgoing is I. So this second junction says that I1 plus I2 is equal to I. So in this case, there is a redundancy. Although I have 2 nodes, 2 junctions, but only one useful equation out of the 2. Either this or this. They're the same equation, as a matter of fact. Algebraically, it's the same thing. So there is always redundancy when you're dealing with Kirchhoff's rules. There is always one too many, okay? So there is always, you have to be careful with that problem. The same thing is actually true with the loops. Okay, let me tell you why we have too many loops. We have loop number 1. I could take any starting point. It doesn't matter where I'm going to. It's a good idea usually to take it immediately next to the battery. You don't have to, but you can take it anywhere you like. Okay, so here is the loop. So I'm gonna go around, go through my closed switch, go through my resistor 5 ohms, come this side, but decide to come through this 5 ohms, and then come back, now go around the battery, and I'm back into here. So this is loop number 1. Loop number 2, I can go from this junction through the resistor of the 10 ohms, and then come back. Going through this point in here, the second junction, and come back through the 5 ohm and straight back in. So I have 2 loops in here. There is actually a third loop in here. I can take the starting point or any other point. Doesn't have to be this one. Go through my switch, go through my 5 ohms, and then instead of going through the other 5 ohms, I'm going to go through the 10 ohms, come through the other junction, and come back through the battery, and make it through after the battery and back to here. So I have 3 loops. But again, there is a redundancy. Actually, you only will have 2 equations out of these 3 loops that are useful. The third one will be basically combination of the other 2. So that's the only caveat when you're dealing with Kirchhoff's rules, is that you will have more equations than what you need to solve problems. That could be a good thing, but that could be also a bad thing if you probably do mistakes. The only good thing about it, honestly, is to check your answer. Remember, I always ask for a discussion at the end of solving problems. This is a good way of doing it. Okay? You do things using 2 loops, for example, and to check yourself, if you did everything correctly, go to the third loop. Does it still hold true? Does it still say that the drop in voltage is going around is the same? It's 0, actually. You didn't gain any height, you didn't lose any height. If you go to another junction there, for example, does it still add up the currents to be 0? If they don't, then there is something wrong in the algebra. So that is a good way of actually generating some discussions at the end to say, instead of, okay, it makes sense, how does it make sense? Oh, I took another loop. Here is another loop that I didn't use in my equations, and it still verify the loop equation for it. So that still makes sense. Do you understand? So my answer looks like it's consistent at least with Kirchhoff's rules. Do you guys understand? So you always end up with 1 too many, only exactly 1, not more than 1 actually. So in this case, I only have what looks like 3 loops, but in actuality, I only have 2 independent loops. The other loop is actually a combination of the other 2. Same thing, I seem to have 2 junctions, but as a matter of fact, it's only 1 useful junction. The other one is just a repetition of the first one. There is a redundancy always. So if I give you a far more complicated circuit and you look like you have so many junctions, and it's probably true, and so many loops, and it's probably true, but at the end, remember, you're going to count just 1 less than what you should have. That is the practical way of doing problems. Okay, so let's do this problem now, and let's answer the problem. Now, I know, since the question was asking me for the power going through the 10 ohms, that power must be given by R, which is 10 ohms, times the current squared that goes through it, okay? So I better find that current I2 squared. So if I don't know I2 squared, I don't know anything. So I go back into this equation, and I2 is clearly I minus I1. But I don't know what I and I1 is, so I have 3 unknowns in my equation. I want I2. So I need a bunch of other equations. So let's take loop 1, okay? I go from my starting point, and I find this point in here. This is the 0 drop, because the resistance of a closed switch is 0. So it's going to be 0 times I, which is 0. And here I have 5 times I. And I'm going in the drop direction. So it's going to be a positive number. When you're dropping, it's going to be a positive gain, if you wish, of energy. So it's going to be 5 times I. That's Ohm's law. Then I decided to go through the other 5 ohms. The other 5 ohms is 5 times I1, because I1 is the one that is running through the other 5, not I. So plus 5 times I1. Now, here's the problem. I'm going through this battery now from the lower side, from the negative side, to the positive side. Think about it. You're dropping a potential by 5I. You're dropping a potential in here by 5I1. And you're rising in potential now by 12 volts. So this expression is keeping track of how much you dropped. So this is a rise, therefore it's a negative 12 is equal to 0. Okay? So practically now, I have one equation with 3 unknowns. Okay? I have another equation with 2 unknowns. So algebra, if you took algebra, and I think some of you already did probably linear algebra, I don't have enough equations to solve my system. I have 3 unknowns in 2 equations. I need at least 1 more equation to solve the problem. So now I have choices. Either I take loop number 2 or loop number 3. So once I take one of them, I don't need the third one, because I will end up with 3 equations with 3 unknowns, and that's enough for me to solve the problem. So that's why I was saying that there is a redundancy also in the loops, because if I take loop number 2, then loop number 3 becomes useless, becomes redundant. I use it to check things later on if I want to, okay? If I take loop number 3, then in this case, loop number 2 will become redundant. I can use it later on to check things for me. So let's take loop number 2. Loop number 2, my starting point is this node. And again, I chose it clockwise. So let's stick with the clockwise, okay? I could have done the other way around, and there is no rule to tell me that you choose clockwise or counterclockwise. I can do whatever I want to, as long as I'm keeping track of the signs, though. Am I gaining or losing potential? I'm going higher or lower in potential, that's all. So if I follow the current, I'm dropping. Because I drew the current I2 pointing down, that means I'm dropping by 10 times I2. So since I'm keeping track of how much I'm dropping, so it's going to be 10 times I2. That's correct. But now, when I come through the other side of the 10 ohms, there is no device, and I'm going straight out through the other node back to the starting point in there. Now, when I do that, I'm going against the current. I1 is coming down, and I'm going against it. So I'm rising in potential. So it's no longer a drop. So if you wish, it's a negative drop. Negative drop by 5I1. So it's a minus 5I1. By the time I reach the starting point, where I started from in this loop, I am at 0. Okay? So the whole thing now is equal to 0. So now I have enough equations to solve my problem, okay? I have these 3 equations, I equal to I1 plus I2, which I can use immediately to get rid of I. And then I will end up with 2 equations with 2 unknowns. So the third equation doesn't have I in it, okay? So I'm gonna use this equation here to get rid of I, because I don't need it. They didn't ask us for the current that is being drained from the battery. So there is no need to go through. I mean, if somebody asks you at the end, you can go back and find it. But at the end in here, at this point, there is no need for it. So I'm going to take I and sub it in the other expression. And the second equation then becomes 5 times I1 plus I2. Okay? That's this term, 5I, plus 5 times I1 minus 12 is equal to 0. And the last equation, I'm going to just rewrite it because it doesn't have an I in it. So it's 10I2 minus 5I1 is equal to 0. Now, my goal is, first of all, there is some business in here that needs to be taken care of. 5I1 plus 5I1, that's 10I1 plus 5I2. So I need to group the terms to do some cleaning in here because there is some cleaning in order for the first equation. I have 5I1 plus 5I1, that's 10I1. And I have 5 times I2, that's 5I2. And the negative 12, I'm going to take it to the other side to write just 12 on the other side, okay? Now, I have 2 equations with 2 unknowns to solve. Remember, my goal is to find I2 because the question was specifically trying to find the power dissipated in the 10 ohms. That's how they want. That's the question, okay? Let's not lose track of that because that's going to help me focus, okay? So I want to find I2. I can use the first equation, which is after I simplify again by 5, I'm going to end up with 2. So 2I2 is equal to I1. So that's what the first equation is. So it says I1 is equal to 2I2. Okay? Basically, 2I2 is equal to 5 minus I1 is equal to 0. So I just moved around. Now, I take this I1 and sub it in the last equation. And now I end up with just one equation with one unknown. So the last equation is 10 times I1, and I1 is 2I2, by the way, plus 5I1, 5I2, that's what is equal to 12. So now it's just a matter of getting terms. 2 times 10, that's 20, plus 5, that's 25. So 25 I2 is equal to 12, and the answer then is 12 over 25. I2 is 12 over 25 amperes. Okay, remember everything is in volts and everything, so at the end the answer is going to be in amperes. So if I multiply this number by 4, that's going to be 100, and this number by 4, that's going to be 48. 48 divided by 100 is 0.48 amps. So that's the answer in terms of current. I really don't care for the current. I want to find the power. So the power is going to be P is equal to 10 times 0.48 squared. If I do it quickly with a calculator, because I don't want to do it, spend too much time with my hand on it. So 0.48 squared times 10. So the answer is 2.304, if you like to be more specific, 2.3 watts. Okay. So that's the power that is dissipated in I2. Of course, you know, guys, now that we can answer anything about this circuit. If you are curious trying to find what I1 is, this I1, use this expression. Where is it? I1 is twice I2. Since we know what I2 is, 0.48, that's just multiplied by 2. If you're trying to find how much current is being drained by the battery, from the battery, then in this case, the battery is draining I1 plus I2, 0.48 plus twice 0.48. So it's going to be 3 times 0.48. So that's really what the total current is. So it's going to be 0.48 times 3. So that's the current that is coming from the battery. It's a good idea to know that number because ultimately, so it's 1.44 amps. Okay. And if you're curious trying to find how much power is actually taken from the battery, how much energy is being drained actually from the battery is 1.44 times 12 volts. Okay, so the battery from that we take from, remember it's a 12-volt battery. The 12-volt battery taking we're draining from it 1.44 amps, so 17 watts, 17.28 watts. So again, 2.3 of it only is going through this one, and some other stuff is going throughout the circuit in there. So the power from the battery now is the EMF of the battery, which is 12, times the current that is running through the battery, which is it turns out to be I1 plus I2, and that is 1.44 amps if you do the calculation. Okay, and this is 12. So the whole answer was 17.28 or something like that watts. Okay, so again, you can answer anything about the problem using Kirchhoff's rules. A good question in here to ask is, does this still make sense? Of course, if you go through the voltage drop and see from the 5 ohms, how much drop did we really do? Okay, well, the drop from the 5 ohms is 5 times the current I, and the current I is I1 plus I2, and I1 plus I2 is equal to 3 times the other number. So let's calculate it. So let's remember, I found 1.44 times 5. 1.44 times 5, come on, calculator. My calculator is not responding in time. Okay, finally. Sorry, it's taking forever. It's giving me black screen. Okay, so the drop in the first 5 volts, okay, 1.44 times 5. So that's 7.2 volts. Remember, the whole battery is 12 volts, okay? So when you're doing calculations like this one, you cannot have a device in your circuit so there is a 12 volt drop in here. I mean 7.7 volts. Is it 7 or 7.2? I need you guys to verify this number. 7.2 volts. That's 5 times I. Okay. Now I'm gonna go through the third loop to verify things work. Okay. 10 times I2. I2, remember, is 0.48 times 10 is 4.8 volts. Okay. So I dropped by 7.2 and it dropped by 10 times 0.48. So it's going to be 4.8 volts. Add up the numbers in here. So I have, that's going to add up to 12 volt, doesn't it? So I dropped by 12 volt and then I rise by 12 volt. So at the end, I end up with nothing. So I dropped by 7.2 through the third loop and I dropped by 4.8 and there is nothing I encounter in here going back by negative. So this is how the algebra through the third loop now look like. The third loop now has a 7.2 drop volt. The 10 ohm, which is the outside battery, has outside the resistor has a 4.8 volt drop. That's 10 times 0.48. And the battery has a rise of 12 volt. So at the end, I should add up to nothing. I should have nothing through the third loop. And indeed it does. Okay. Does this example make sense to you guys? I suggest that you go through and you work all of these things in there. Because you have, this is a good example to start with and do all of your circuits in there. Does it make sense to you guys?
Yes, Professor.
Okay, I really urge you guys to go through this entire process. We're given a battery of 12 volt. We're given 3 resistors, 2 5 ohms and 1 10 ohm. And the configuration was that the 5 ohm and the 10 ohm were actually in parallel. And we ended up basically using Kirchhoff's rules and finding the currents everywhere, not just in the 10 ohm, because the question was for the 10 ohm, the power, all we needed there is its current to square it and multiply it by the resistor, and we would have been in business. But I went a step further. I wanted to know how much power is actually drained from the entire device, from the battery. It turns out to be 17 watts. And also check Kirchhoff's rules to make sure it works for the loop that we didn't use, loop 3, because if we used it, it would have been just a combination of the other 2 loops. Same thing with the nodes. We ended up with 2 nodes and only we used one of them because the other one is identically the first one in terms of mathematics. So that summarizes a lot of things about what we're doing. Here is the big deal of this chapter, okay, that will have tremendous implications for your homework and your also lab for next time around too, and also for your exam. and that is the capacitor and a resistor combined together in a circuit, the so-called RC circuit. So let's introduce that that idea and see how that works, okay? Can we mute this thing in here? Okay. So here's the point. I have a battery and it has a certain EMF, okay? Usually it's a good practice to have a switch in a circuit, okay? And then, as a matter of fact, I can do it differently, okay? I'm gonna put the switch differently. I'm gonna put an AB switch. So I have in here another wire. This is position A, this is position B. And this is where my switch is. This is a two-way switch. It can be in position A or position B. Now, I have a resistor R. Okay, followed by capacitor C, and close the circuit. If the switch is open, there is nothing happening. Nothing, okay? Like this. Now, if I put it on B, and if the capacitor has no initial charge, then there is nothing also that's going to happen because there is no power source for the circuit, for this loop, basically. There is nothing happening in there, okay? But if I put it on position A, then a current starts to flow and charge start to accumulate on this side of the capacitor, okay? And charges will be drained from the other side. That is if it's in position A, okay? And the charges continue to accumulate, and as they accumulate, voltage will build up across the capacitor, and that voltage will start to, because now this is the positive side of the battery always, the longer one. So this will start to basically work against the battery until there is a lot of charge sitting on the capacitor that is going to work against the battery and actually stop the current from flowing anymore, okay? In other words, there will be enough energy in it to basically balance the energy coming from the capacitor, from the battery, and at that point the current stops. So initially, since there is no charge in the capacitor, you can build current as fast as you want. So there is a lot of current going through the resistor. But as time goes by, the charge now is building charge, the capacitor is building charges in it, so it starts to oppose the battery, in which case it's going to stop completely the battery from pushing any more current. And that's going to stay there. So how long does it do that? Takes that? I'll give it enough time to do that. We're gonna give it t equal to infinity. Okay, we're gonna give it an infinite amount of time to do that, okay? To charge the capacitor. So when the switch in position A, we are actually charging the capacitor. So when the switch in position A, that is charging the capacitor. Okay, we're done. At some point, we decide that the capacitor has charged, okay, charged enough. How long that time, we will discuss it. We will know what's the time needed for the capacitor to be satisfactorily, and that's the word to be used in here, charged, okay? The key word in here is to our satisfaction, okay? Then we decide, you know what, we're going to switch the AB switch back to position B now. If the capacitor now has a charge, and we switch back to position B, now the current starts to flow in the opposite direction through the closed circuit from here back to the capacitor until the capacitor runs out of steam, or out of energy. So at that point, the current also stops, okay? So when we are in position B, we are actually discharging the capacitor. So you work with the emergency, what is it? The people who give them the ambulance, and you have those things. So they are fully charged now, and there is a patient, so you put them on his heart, and at that point you discharge the capacitor. That's actually capacitor that you're using there. And then you build enough charge and then discharge, charge, discharge, and basically that's what the process is. Or you have a flashlight, the same thing, you build enough, not the phone ones, the phone one is different process, but at least the old ones for the cameras, is again, you build a lot of current in the capacitor and you discharge of it by having that immediate basically charge that comes out, and then you build capacitance again and discharge it. So there are a lot of practical uses for this one. Sometimes it's used actually in circuitry, trying to safeguard it from complete current going to zero immediately, and that is you have in next to the power supply usually capacitor to hold some of the energy just in case if there is a power outage or there is a problem in the circuit, for example, the current drops below a certain level. Now you drain energy from the capacitor. So the capacitor is used as a backup basically system to prevent the system from going to immediately to shut down or to be used actually for discharges and things like that. So this is what we're learning. So this is what we want to do. We want to take the first stage is to charge the capacitor, to put charges on it. And we're going to calculate how much energy now is stored in the capacitor. It's easy. It's how much charge you have at the end divided by 2, charge squared, that is, divided by 2c. So all we have to do is add up all of the charges over time and say this is actually how much we have, okay? And of course, we want to know where did that energy come from? Where would the energy come from? Would you guys suggest in here? I have a circuit with a battery, an AB switch, a resistor, and a capacitor. Where is the suspect? Who do you think will give us the energy that we're going to store in the capacitor? Any suggestions? Where do we get the energy from? I mean, there are only 3 culprits, either the battery or the switch or the resistor. Where do we get the energy to charge the capacitor from? Come on, guys, you tell me. Okay, some of you are. Yeah, that's the obvious basically choice. It can only be the battery. Resistors don't have an internal energy. As a matter of fact, resistors are notorious to waste energy, okay? So that's not a good source. The switch has no resistance, has nothing. So it's just basically acting to help us basically switch from one position to the other. So the only source is the battery. So I want to know how much did we actually drain from the battery and do a full account of the energy, okay? We have to keep track of every single joule, okay? So if we took 15 joules from the battery, did we get it all in the resistor, the capacitor, or did some of it get wasted in the process, okay? And if it gets wasted, how much it was wasted? Same thing. Now we have a certain amount sitting on the capacitor, so when we were discharging it, where did it go? So let's go back into the switch when we are back in AB. So this discussion is going to be finished on Monday, I guess. So when we are now closing the circuit in position B, then in this situation, we are actually going to have the charge go somewhere. So again, the wires don't take anything. The switch doesn't take anything. So the only culprit is going to be the resistor. So when we discharge, we're going to lose energy from the capacitor. So what that energy goes, it's going to go ultimately in the resistor. So we need to do an energy full tally of where the energy is at. Okay, here is a promise. Come Monday, we're going to finish this part in the lecture. We're going to talk about the meters, basically, electrical devices used for measuring things, namely the voltmeter, the ammeter, the ohm meter, and also the potentiometer, which is actually used to measure the potential, the batteries, basically EMF. Okay, and but most importantly, we're going to go through the process of charging and discharging a capacitor. We're going to spend the entire period doing these calculations, and it's a good idea to refresh your minds on doing some integrals, okay? Because it's going to involve, because this is a time process, so we need to do some integrations at some point, okay? It's going to be a very simple integral that I'm hoping that you guys should not have difficulty with. So this is where we stand in terms of lecture. We are midway in chapter 26. Hopefully we'll finish it in Monday. And by then we will have a full coverage of everything. Come Tuesday, we're going to Wednesday of next week, we're going to start chapter 27. And the Monday after is going to be all reviews. Okay, the Monday after is going to be all reviews. The Monday of the 12th is going to be all reviews. Namely, we go through the problems like we did last time. We go through all of the review problems. We discuss them. We make sure that everybody is happy with the way to tackle these problems. Come Tuesday night at 10 p.m. basically is when the exam should be available for you guys. And you should be able to deliver it by Wednesday morning on the 14th. Okay. So this is where we stand. And then on the Monday after, which is I think the 19th of October, we're going to finish chapter 27 and continue with chapter 28 on the 21st. So this is where we are right now in terms of content. Any questions? I strongly urge you guys to go through that example. It's a simple example, but I'm hoping that you guys can go work your way through it because it has a lot of things in it. I mean, even that simple example has a lot of calculations in it. So that is basically typical of circuits. But once you get the hang of it, you're going to enjoy them. Once you really know how you're doing it, you're going to enjoy this kind of problems. Carlos, were you going to say something?
I'm all good, Professor. My apologies.
Okay, no problem. Okay, guys, I'll see you Monday, same time. Please catch up. You have a lot of homework that is due on the 10th. Don't forget that too, okay? And do ask. I proposed something for you guys and nobody answered it too, and that is to do homework problems on Wednesdays outside of the time allocated, and nobody answered. So it's still open. The offer is still open, okay?
I thought you said it was lecture, Professor. An extra hour of lecture before class
No,
on Wednesday.
no, not a lecture. I'm sorry. It's to do problems. That's it. Did I say lecture?
Oh, yeah. You posted that. You sent an email saying that. Oh, extra. We will be going. You said you would be going over problems, but you said lecture.
Before lecture time, probably that's what I meant. I'm sorry if you guys understood it lecture. No, there's enough lecturing. We need more time for doing problems.
No, that's fine. So
Okay,
will it be every Wednesday before class, or?
if you guys choose to, so I'm available, so I'll open it and then we will go through the problems from the homework. It's going to be your session. So if you want me to we work together through the problems and basically answer them, make sure that your homework problems are done and extra problems and things like that to basically help you prepare and do things. So the offer still stands. So if you guys want to, we will meet and I will be more than happy to do that every Wednesday before lecture, okay? That because we meet on Wednesday, like today, and the hour before lecture, we meet and basically talk about the problems and which problems you would like to talk about, which problems you would want to have them discussed more and things like that, okay? So the offer still stands.
I just did not. Yes, sir.
Okay.
Good.
Okay, if you did not know how to reply, you could have, okay, that's fine. Just basically let me know, please, okay? I'll be more than happy to send you an invitation, everybody, or open a new session completely, and we will do that. Thank you, Daniel. Sebastian, hopefully you're going to be on. Carlos, everybody else. See you guys.
Take care, Professor.
You too, bye.